In our previous video, we explored dehydration of alcohol. And now we're going to explore dehydration of vicinal diols. Vicinal diols are also known as glycols. It's called the Pinacol rearrangement. First one, it's not obvious what rearranged, but I hope you see in the second one that a methyl group rearranged. The second product. Here the methyl group is carbon 4 compared to dimethyl on 1. 1, 2, 3, 4. Yeah, here the methyl's on carbon 3. 1, 2, 3. Yeah. So, got a question for you. Why does it? Yeah, it's right here. Extra questions. Why does the tertiary alcohol dehydrate much faster than the secondary? Well, tertiary alcohols, if you make them into good leaving groups, can become what? The thing leaves. What are you left with? Okay, water's the leaving group. But when it leaves, you're left with this. What's that? Carbocation. Re-look at the question now. If you're making a carbocation, why does the tertiary alcohol dehydrate much faster than the secondary? Sorry? You're comparing what happens to the tertiary alcohol, which we just talked about. What does it become if you protonate it and then the leaving group leaves? Carbocation. Please answer the question now. Why does the tertiary alcohol dehydrate much faster than a secondary alcohol? Because it will make a more substituted carbocation, which is more stable, which is easier to make. I think I can write that down. Because it makes a tertiary alcohol. Clearly, the machine does not understand me very well. It did understand that. All right, I'm just going to write it down. Question 1. Because a tertiary C+ has more hyperconjugation than a secondary C+, it will form faster. So if it's forming faster over the same amount of time, there's going to be a higher number of tertiary carbocations compared to secondary. So in your mechanism, please consider both carbocations. Tertiary carbocation has more hyperconjugation than a secondary. It will form faster. We'll do the tertiary mechanism first. Since it happens first, step 1, make it a better leaving group. Oh, you don't have the right activity? We'll put a pause on this one. And here, as I said in the off the video, I don't like paper. So we're back to here. Everybody's finally got activity 2. We protonated it. What was the purpose of protonating it again? To make a what? A leaving group so that it can, yes, leave. And you get a lovely tertiary carbocation. Tertiary carbocations, until today, you thought those were the best. Until today. But apparently there's something more important than hyperconjugation. Because question 2 asks, what is more important than hyperconjugation for a carbocation stability? Well, let me make the Pinacol rearrangement happen first. That's when we shift an atom adjacent to a carbocation or vicinal towards the carbocation. And we're going to make a secondary cation. You're going to say, wait, he said that wouldn't happen normally. You would have a good argument if you didn't know there's something more important than hyperconjugation. Here's an O that happens to have 2 lone pairs, but I only need one of them for the answer to question 2. What can this carbocation do that the one before it could not in terms of stability? I'm sorry? What can this cation that I just circled do that the one prior to it could not? And the answer to the question I will give you non-verbally right here. What arrow is that? It's the answer to your question. Resonance is more important than hyperconjugation. Why? Simple reason. This species has a total of 0 octet violations. No OV has an OV. That's why carbocations are so darn hard to make. They have an octet violation. Well, if you can make one that can resonate to not have an octet violation, you are home free. So what is more important than hyperconjugation for carbocation stability? Resonance. Here's how it happens, and here's the final product. I want to remind you, in step 1, we made TSO minus, and look at this thing, and look at this thing, and tell me what's the only thing that has to change. Remove the H from the oxonium to make the final product that's listed first. And TSO minus is going to do that, and the cat's going to scratch at the door and go meow and say, I'm back. Because you got TSOH, right? Also known as hot. There you go. Okay. Before I do the other product, I'm going to show you a time saver that gets you the same product here from this point directly. You can combine resonance with any other reaction that either precedes it or antecedes it, which is like after. So I'm just copying that molecule as I see it. And what we have here is a beautiful resonating carbocation. And instead of resonance followed by acid base, I'm going to start off with the acid base. With the OTS negative. Grab H. This is E1, by the way. What has to happen for me to finish? This is confusing here. I don't like it. I got a better way to show it. That was that going to the final product. This is different way to get to the same place, but not really. It's the same way. It's just shorter. Tell me what else has to happen. The bond between the O and the H becomes a pi. Done. Isn't that nice? You saved it in drawing this resonance form. You didn't have to draw it in the first place. So when I do the other product, I'm not even going to show the resonance and then the acid base. I'm going to show you straight up from the rearranged cation how to get to this product. But before I do that, I got to realize that the other O is missing here. You realize that it's the bottom O that's missing on this one? This O is missing on this one? So you better protonate this, because the O that's missing, how did you get rid of it? You protonated it and it left. So start the mechanism over. You need another copy of the original molecule. Another copy. Do not try to find a shortcut that shows me a molecule doing two different things. I've already made statements on that before. This is start over, use HOTS again, or no, sulfuric acid again, sorry. HOSO3H on the bottom alcohol. Make it a better leaving group. This is going to be slower. You know this, right? What did you do after you made the first oxonium? Right here. What did you do to it? Make it leave. Same story here. The steps are no different. I'm going to go straight to the shortcut pretty soon. Make it leave. Make it leave to a cation. Secondary. And then take a look at that product we haven't done yet. This one, what has to move from here to have the same skeleton as up here? The methyl moves from this carbon to the adjacent position. We've been doing that since our test 2, right? And now you're at the stage where you're at the stage where you've got methyl here, OH cation, and I want to go straight to the final product without doing the resonance as a separate step. So do you see how you're at the equivalent of this stage of the mechanism? Down here, your base is going to do what on this one? Grab which H? The one on the O, attached to the cation. OTS negative. We never had OTS negative. Never had OTS negative. It was O negative with SO3H. O negative with SO3H. Same story here. O negative with SO3H. Grab H. What's my next arrow? From the bond between the O and the H to a pi between the O and the C. End of story. Doesn't ask for major or minor, but this would be a minor cation compared to the major cation. which means the major product comes from the major cation. The minor product comes from the minor cation. They're both resonators. I like that. But if you had to choose between a secondary resonator and a tertiary resonator, the resonance is the most important thing, but that's constant between the two. You got to pick the one that's secondary over, it's tertiary over the secondary. They both said, wait, they're the same. If I had to compare the stability of this to the stability of this, I'd say I can't. They're both resonating. That's the best thing. They're both secondary. Second best thing. So there's a dead tie. Now you got to go back to the original cations and ask yourself which one formed first. This one that came from water leaving this, or this one that came from water leaving this. So which of these two formed faster? That is question 2, by the way. Question 1. Why does the tertiary alcohol dehydrate much faster? Well, it's because this step makes a tertiary cation compared to this step, which made a secondary cation. They both rearrange to beautiful cations of equal stability. So you can't say that as part of your answer, but the original cations are why this one happens faster. And that's enough for that video.